So folks, let's put two pieces together. In the first video, we looked at a double integral over some rectangular region R. So the way we thought of this was a tool to compute net volume. You don't need to write this down. And the way we did it, we looked at taking a little dA, a little bit of area, and multiplying it by a height. So we formed a column whose height was chosen by selecting some point in the original rectangle in the domain space, plugging that into a function, and giving us a z-coordinate for a height. And so we thought of volume as taking a height times an area. And in this in the next example, we looked at iterated integrals, which maybe look like the integral from a to b and then c to d of f of x, y, dy dx were the examples that we saw. And the way we looked at that was what we were doing is we were taking for a surface given by f of x, y, is we were taking some cross-sectional piece of that surface, computing the area of that, and then doing that all the way throughout over some particular region. We're going to develop that much more carefully in class. But again, the idea was we were going to take a cross-sectional area, and then we're going to multiply that by a small change in width. And that's going to give us the volume. So we've got the double integral and the iterated integral. So you don't need to write any of that down. So similar to how the fundamental theorem of calculus made evaluating Riemann sums, these infinite Riemann sums, a lot easier, Fubini's theorem allows us to compute iterated integrals, which are far easier to compute, instead of computing double integrals. Okay, so I want you to think of, in one way, Fubini's theorem is sort of as important in Calc 3 as the fundamental theorem of calculus was in Calc 1. So what does Fubini's theorem say? Here it is. It says, suppose f is continuous on a rectangle. By the way, this is actually a little bit misleading. You can relax that requirement. But that's a topic for another course. But anyway, you've got a function that's continuous on a rectangle. Then what this says is that computing this double integral, this is a double integral, is the same as computing either one of these iterated integrals. That's really helpful. Rather than computing a difficult double integral, the way we'll see how to do in class, we can compute these iterated integrals instead, which you've already learned how to do. There's one other thing that's really important about Fubini's theorem. And what we see here is that evaluating the iterated integral, where we first find the integral with respect to y, and then we take the integral of that function with respect to x. If Fubini's theorem applies, that's the same as first, oops, I have a mistake here, folks. I will change this for your notes, but this should be dx dy, which says we could evaluate first with respect to x, and then with respect to y. So Fubini's theorem tells us that as long as f of x, y is continuous, at least for this class, then we can interchange the order of integration for our iterated integrals. That's really important because sometimes integrating with respect to x will be far more difficult than integrating with respect to y, or vice versa. So, for example, I'd like to go ahead and work this problem here. So, just to give you a visualization, we've got a function, in this case, our f of x, y, the surface, is the surface x e to the xy. Okay. So I didn't actually draw this surface here. I'm just depicting it sort of generically here. But what I wanted to highlight in this problem was a couple of things. And the first thing was, let's actually talk about these regions in the xy plane here. So first of all, you can see that the x values go between x equals 0 and x equals the natural log of 2. And that's what we said here. Similarly, our y values go from y equals 0 all the way up to y equals 1. And that's what we saw here. And that constructs a rectangle. So this is our region R. So anytime you hear about our region R, it's essential that you remember that R is in the domain space, in this case in the xy plane. So here we go. We're going to try to compute the integral, the double integral over the region R of x e to the xy dA. This would be a bear to compute on its own, but luckily the function x e to the xy is continuous everywhere, in fact, but specifically it's continuous on the region R that we're talking about. And so that means Fubini's theorem applies. This means I could write this as the integral, and go ahead and bear with me, write it this way first, from x equals 0, from y equals 0 to y equals 1 of the integral from x equals 0 to x equals the natural log of 2 of x e to the xy dx dy. What did we just apply to be able to rewrite this double integral? That was supposed to come out red. What did we just apply to rewrite this double integral as this iterated integral? Well, we just applied Fubini's theorem, so I would add that. That was by Fubini's theorem. Okay. Now, if you're at all curious, I challenge you to try to evaluate this iterated integral. If you're interested, I tried, and I got stuck, and I plugged into my math lab, or a Mathematica. But you can see my partial work there as we got through, and we arrived at, with the machine's help, I arrived at a solution to this. The problem is that if I go to integrate this with respect to x, you guys can already see, hopefully you remember from Calc 2, that because I've got x e to the xy, I'd have to integrate that using the technique of integration by parts. And I'm not saying that you won't ever have to use this regardless of your choice of order, but generally we try to avoid it if we can. And in this problem, even though we could evaluate this first integral with integration by parts, the next integral after that will be complex as well, and we'd have a hard time with it. So what I'm going to do is I'm going to change the order of integration. And again, if you don't know why, try to evaluate this integral here as it's given and see how far you get. So I'm going to interchange the order of integration here. And that's going to make our lives significantly easier. Well, that's fine. I guess we'll leave that. So there's our dy. And so I'm choosing to think of the iterated integral this way, where I'm going to integrate with respect to y first, and then with respect to x. And that's what you're going to have to learn. And to be honest, there's no real set of steps to learn that. That sometimes you might try to integrate with respect to x first and see that it's going to be a mess. So maybe it's worth trying to integrate with respect to y first. Other times maybe it's just messy no matter which way you do it. Or maybe it's easy no matter which way you do it. So anyway, integrating with respect to y first. Well, the integral, so I'm going to fix that x as constant. And so really this is just a constant times e to a constant times y. And so when we integrate, we have x e to the xy, and then by the chain rule we'd have to divide by a factor of x. If you don't believe me, just take the derivative of this expression and see that you'd be back to x e to the xy. So let's clean that up just a little bit more. That goes from x equals 0 to x equals the natural log of 2. That's of e to the xy evaluated between 0 and 1. Sometimes I'll get sloppy and won't write that y equals. So now if we evaluate that, this gives us the integral from x equals 0 to x equals the natural log of 2. Again, I'm just kind of leaving that outer integral alone as I work with inside that inner expression. But if I plug in a 1 for y, that's going to give me the function e to the x. And I'm going to subtract from that the same function e to the xy, but plugging in a 0 for y. And that's going to give me 1. So now we're ready to integrate this again, this time with respect to x. So integrating with respect to x, e to the x integrated with respect to x is still e to the x, and negative 1 integrated with respect to x is minus x, evaluated from x equals 0 to x equals the natural log of 2. So if we go ahead and plug everything in, this is going to give us, for the upper limits of integration, 2 minus the natural log of 2, minus 1, minus 0 if you like. And so we're left with 1 minus the natural log of 2. And there were two things that we wanted to highlight in this problem. The first was that we applied Fubini's theorem, actually twice here, so let me highlight that again. We applied Fubini's theorem to say, rather than evaluating this double integral, which is generally hard to do, because our integrand was continuous, that means Fubini's theorem applies. That's all we need to be able to apply Fubini's theorem. And so we were able to rewrite this double integral as an iterated integral. Additionally, even though we first wrote this as an integral, where we first take the integral with respect to x and then with respect to y, I tried to convince you anyway that it would be difficult to do it that way. So we interchanged the order of integration. And Fubini's theorem says that as long as our region is a rectangular region, we can go ahead and interchange the limits, or excuse me, the order of integration. And so this turns out is a much easier way to integrate the problem. And so we went ahead and did so, arriving at this solution. Again, if you're curious, go ahead and take a look at the partial solution that I gave with the help of Mathematica to evaluate it the other way. And notice we did arrive finally at the same answer. But the second point that we want to take from this example is that the order in which you choose to integrate when you're using an iterated integral over a rectangular region does matter. And so you want to learn how to be careful with your choice. All right, we'll be moving on in the next video. Thanks for your patience. Let me know if you have any questions.